Hi everyone and welcome to our Forum 7 wrap-up. This week we took a look at analysis of variance testing. We used ANOVA to evaluate differences between the means of groups or populations in order to make conclusions about a particular intervention. As a quick review, let's compare analysis of variance to t-testing. Both ANOVA and t-testing have the ability to compare treatment and population groups. However, the ANOVA can compare more than two groups simultaneously, thus allowing greater flexibility in design. With t-tests, you're stuck with two groups and one outcome. ANOVA calculations address the variability between groups to the variability within groups. In other words, how does each group differ from the others, and how do the members within one group differ from each other? Additionally, we also discussed the difference between performing multiple t-tests versus performing a single ANOVA. Keep in mind, the alpha level of a t-test tells us how likely we've made a mistake. In other words, we state that a difference between the groups exists when in reality they do not, i.e. we fail to accept the null hypothesis. So, if our alpha is set at 0.05, we have a 5% chance of making a type 1 error. If we have more than 3 groups, we would have to do multiple t-tests. This would mean we would have to do individual t-tests comparing group 1 to group 2, group 1 to group 3, and group 2 to group 3. Every time we perform multiple t-tests, we multiply our probability of our hypothesis type 1 error. The more hypotheses decisions we have, the more chance that random differences may occur. And this is because each hypothesis has an alpha of 0.05. If we have 3 hypotheses, you will inflate your chance of type 1 error up to approximately 15%. The inflation of this error is referred to as family-wise error rate. Similar to Z and T testing, ANOVA also has its own distribution referred to as the F distribution. We use this distribution to obtain our critical value for determining whether to accept or reject a null hypothesis. Up to this point, we have discussed the different types of curves that are associated with Z, T, and F distributions. So, we have 3 curves right here. If we had to put a label on each one and say which one is the Z, which one is the T, and which one is the F, which would they be? So take a second, pause your computer, and think about that one. Alright, we're back. So let's take a look at these one by one here. So, the distribution all the way on the left looks pretty similar to the one that's in the middle. So how do we tell them apart? Well, the key here is to look at how much space is actually in the tails. So if you remember from the forum discussions as well as the discussions in your textbook, which distribution is going to have more space in its tails, the T or the Z distribution? Well, hopefully you guessed that. So this first picture here has more space in the right and left side of the tails, therefore making it a T distribution when we would compare it to the center picture, which is going to be our Z distribution. And by process of elimination, we only have one distribution left here. That's the one all the way on the right. That one looks like a positively skewed distribution due to the longer tail on the right. So that is obviously our F distribution. Your text and videos discuss 2 types of ANOVAs, a single factor ANOVA and a factorial ANOVA. Our one-way ANOVA, also referred to as a simple analysis of variance, utilizes a single factor that has 3 or more levels. One-way refers to one independent variable. Sometimes we hear about two-way ANOVAs or three-way ANOVAs. This would indicate we have 2 or 3 independent variables, respectively. So in our example on the slide here, exercise is our factor, and we have 3 different types we'd like to compare on the outcome of a timed 40-yard dash. The first group will be performing plyometric exercise, the second group will be performing stabilization exercise, and the third group will be performing no exercise. They'll be our control group. In this example, each type of exercise is considered a level. The illustration on the right provides us with another example of a single factor ANOVA. Our factor is pacing strategies for running, and we have 3 levels. The first level or group is utilizing an alternating slow then fast-paced running strategy. The second group is utilizing an alternating fast followed by slow-paced running strategy, and the third group is performing a steady-state running strategy. A factorial ANOVA provides us with the ability to test more than one factor simultaneously in addition to combinations of factors on a single outcome. It utilizes 2 or more factors with 2+ levels per factor. Here's an example of how they're written at the bottom right-hand corner of your screen. A 2x3 factorial ANOVA indicates that we have 2 variables. The first has 2 levels, and the second has 3. The chart to the left illustrates a 3x3 factorial ANOVA, examining anxiety levels associated with varied degrees of test difficulty. The mean averages are provided at the bottom and right, showing the main effect of anxiety and difficulty, respectively. However, interaction effects can also be calculated as well. Perhaps we want to know the interaction result we would observe in a group exhibiting high anxiety during the performance of a difficult test. This design allows us the flexibility to observe these types of treatment interactions as well. Finally, ANOVA takes a 2-step process to minimize the family-wise error rate and keep our alpha or type 1 error at the 0.5 level. First, it tests for overall significance amongst all groups considered. We look for significant differences somewhere amongst the groups that we're testing. So when we get our output for SPSS, we'll see that, alright, we had 3 groups, and it'll tell us that we have a difference, and it's statistically significant, but we won't know where that difference lies. All we know is that there is a difference between the 3 groups. So that brings us to the second step that we have to perform. Once we've discovered that a difference exists somewhere within our groups, then we can do what's referred to as a post hoc comparison, which allows us to figure out which of the 3 groups might differ from one another statistically. So this allows us to make multiple comparisons without inflating our error rate. So from the forum posts, it appears that all of you are beginning to get more and more comfortable with this material. I hope the on-site session is going well and things are all starting to begin to fall into place. So keep up the good work.